Okay, this is problem 2.12 out of Griffith's quantum mechanics textbook, and it asks us to find the expectation value for x, p, x squared, p squared, and t for the nth stationary state of the harmonic oscillator using example 2.5, which I have here. Now, before I get into this problem, I'd just like to ask if you wouldn't mind please liking the video and subscribing to my YouTube channel. I'm trying to build the channel. I think it has the potential to do a lot of good, so if you wouldn't mind helping me with that, I'd greatly appreciate it. Okay, so this is a very important problem because it uses our ladder operators. And what's interesting is you can write your expectation values of x and p in terms of your ladder operators, which is what we see here. And what we're going to do is use those to actually solve this problem. So let's start with the first part. I guess we already have it here, so I don't have to write it. There is our x and there is our p hat. Now, to find the expectation value of x, then, that's equal to the integral of psi star, the nth state, x operator, psi, the nth state, dx. And since x hat is given there, we can plug this into our integral. So it's the integral of psi complex conjugated. The h bar over 2m omega, I'm going to factor outside. So I'll move these a little bit. H bar over 2m omega. That can just come outside. And then we have our raising operator plus our lowering operator acting on the state psi n. Okay. Well, distributing that, we have our constant out front, the integral psi n complex conjugated, and then times the raising operator acting on psi n plus our lowering operator operating on psi n dx. Now at this point, what's important to know is that when we put our raising operator on our wave function on the nth state, you come back with n plus 1, the square root, times that elevated state. Meanwhile, the lowering operator does something similar, but you just get the square root of n and then psi n minus 1. So it drops us down a state. Okay. Alright, so what do we get here? We're going to apply that to our wave function. So h bar over 2m omega. The integral. I really don't like text mode. I never use text mode, so I don't even know why it's so insistent on popping up. Okay, so for the first one, I don't know why I did a 2. That should just be n plus 1. N plus 1. Psi n plus 1. Then we're going to get plus the square root of n times psi n minus 1 dx. Now what's important to note here is once we now distribute this psi n star like we would here, once we distribute this, we're going to take advantage of the fact that our states were orthogonal. What that means is This product, oops, the text mode again, and this one are going to be 0 because they're two different states. So because of that, this whole integral is 0. This also makes calculating our momentum quite easy. And there's two ways you could go about this. The first is essentially what we did here, only instead of using our x operator, we're now using our momentum operator. And you can do that, but an even easier way to do it is using this property from chapter 1. The derivative with respect to time of our expectation value of x times m is our expectation value of momentum. But of course that's just going to be 0 because our expectation value of x is 0. So its momentum is then 0. Or expectation value of momentum. That's pretty easy. Now the expectation value of x squared, essentially what we're going to do is, well, they actually do it here for us, but essentially what you would do is take x and then have that operate on x. Sorry, my wife is cooking. So in other words, and then you would fill it in. In this case, they actually kind of did it for us, so that's nice. So h bar over 2m omega, no longer square root. And then times the exact same thing. And then you'd have this operate accordingly. So then this is equal to, and this was just in the example problem as well, h bar over 2m omega, our raising operator squared, plus our raising operator acting on a lowering operator, and vice versa. Pretty straightforward stuff. Okay. So now we can plug this into to find our expectation value of x squared. So again, just pull out the constants, the integral of psi n complex conjugated, all of this stuff, you can see this is very tedious, but it gets the job done. And thankfully, a lot of these integrals, thanks to orthogonality, are not actually super complicated. Okay? So, we have all that. Now what we're going to do is obviously distribute this psi and have everything act on it accordingly. So we have h bar over 2m omega, the integral of psi n complex conjugated. And then we want the raising operator acting on the raising operator of psi n, plus, a minus. I'll just write all of this out because if you've watched any of my videos, I make a lot of mistakes because I feel that it's necessary to do it as quick as possible, but we're not doing that right now. Oh, there we go. Okay, so now let's have these operators act on our states. So the first one will give us n plus 1 square root psi n plus 1 plus the raising operator acting on the square root of n, psi minus 1, plus the lowering operator acting on the square root of n plus 1 psi of n plus 1 plus the lowering operator acting on the square root of n psi n minus 1. So real quick, using the same idea of orthogonality and keeping in mind that this psi sub n, complex conjugated, is going to be distributed, you can probably already see from orthogonality that these two n terms are going to be 0, since those will be psi n plus 2 and psi n minus 2. So I'm not even going to worry about those anymore. Okay. So we have the integral of psi n. On the other hand, we have the square root of n, and then we have the raising operator acting on n minus 1. So if you remember what the raising operator does, whatever state it is, you multiply by the square root of that state plus 1. So since it's n minus 1 plus 1 is just n, so it's square root of n psi sub n, which will work now. Plus the lowering operator. So the lowering operator takes whatever state you're in, so first off, n plus 1 square root, times the state we're in, n plus 1, and then lowers it to state n. So we have h bar over 2m omega, and because those are the same states, this is completely fine. We're just going to get n plus n plus 1, which is obviously just 2n plus 1. So h bar over 2m omega, 2n plus 1. Okay. So that part is our expectation value of x squared. And the next one is to find the expectation value of our momentum squared. So that's what we need to find now. So then, this will be minus h bar. Let's remind ourselves up here. H bar m omega over 2. The raising operator minus the lowering operator squared, which is obviously just now everything that we just did we're going to do again, but with these new operators. So we'll have minus h bar m omega over 2, and the integral of psi n complex conjugated, and it's going to be pretty much the same thing. So we have the plus and then minus just distributing our operators plus a minus squared psi sub n dx. Now once again, these terms are going to give you 0 because they're going to drop our psi to psi n minus 2 or psi n plus 2. And because of the orthogonality, that's not really going to work. So now I'm going to factor out the negative, and we'll have h bar m omega over 2, the integral, psi n. And now it's a plus a minus plus a minus a plus psi sub n dx. So we really only have that one to work with, and we actually have already done this one, because what you'll notice is it's just these cases. So that's actually kind of nice. So then we have h bar m omega over 2, times, and then what did we say it was? 2n plus 1, I think it was. And that is your expectation value momentum squared, of momentum squared. Now to find the expectation value of your kinetic energy, again, we can actually just use an earlier theorem, which says that it's the expectation value of p squared over 2m. Well, all we have to do then is divide this by 2m. So that'll cancel the m at the top. That'll be h bar omega over 4, 2n plus 1. So the expectation value of your kinetic energy is pretty easy. And then to find your standard deviations, so that'll be sigma x is the square root of the expectation value of x squared minus the expectation value of x squared. And we already found those, so what was it? This one was 0, and the expectation value of x squared is, I believe, right here. So we would want to take the square root of that, so that's fine. So that would be, I love going back and forth, h bar over 2 m omega, I guess square root, times 2n plus 1 square root. And then the momentum will be essentially the exact same thing, or the same idea. Once again, this is 0. So then our expectation value of momentum will be h bar m omega over 2 square root times 2n plus 1 square root. And then we want to see what sigma x, sigma p is to make sure that our uncertainty principle holds. So we have h bar over 2 m omega times h bar over m omega divided by 2 times 2n plus 1 times 2n plus 1. All of this is under the square root. Just give myself a little space. Okay, well, the m omega here's cancel, so that's great. This cancels with 1 here, and we're left with what? Oh, and this 2 cancels with 1 here. So that is h bar squared times n plus 1 squared, square root, which is h bar times n plus 1, and let's see, this needs to be greater than or equal to h bar divided by 2, which it is, assuming n is just some natural number. So that should just about do it. This is using our ladder operators to work out expectation values. Hopefully that was helpful, and if it was, please leave a like and subscribe. Thank you.